Welcome back to our fifth lecture in probability review. In this lecture, we're going to look at multivariate probability distributions and random vectors. We will start by looking at random vectors and the general notion of distributions of random vectors, and then we'll look at some specific and important multivariate distributions. Okay, a random vector is really just a generalization of the notion of a random variable. In this case, it's an ordered set of these random variables. So for instance, if we have a random variable x1 and a random variable x2 and all the way up to xk, we can put them in a set and call that a random vector. Typically, we use the notation of bold case capital letters to represent random vectors. And in this case, as you can see, it's a column vector. The transpose operator turns that row into a column. So we use functional notation to represent the density functions and mass functions for random vectors, just like we did for random variables. But in this case, of course, we have a bold letter. This is a lowercase x, which represents the value of the random vector. So this again is a vector that's representing the value taken on by that particular random vector. If we were to complete this notation, we'd have a subscript on the f that represented the random vector, and the lowercase x represents the values. But typically, we just leave off that subscript since we know it must be the random vector associated with those values. We let E represent our expectation notation as we did for random variables. Now we have random vectors. So the expectation of a random vector then is as shown. This is again short notation. We can do subscripts that indicate the probability distributions over which we're taking those expectations. And in some cases we'll use that when there might be confusion, but generally it's understood. It's also the case that we can use the fact that the expectation operator is monotonic and that we can take it through a summation. So the expectation of a sum of random variables is a weighted sum in this case, is just the weighted sum of the expectations. Finally, as we think about distributions for random vectors, it's important to talk about the variance. And in this case, we have a matrix. So the variance of the random vector x then is actually the outer product of expectations, in particular the expectation of the outer product of x minus the expectation of that random vector with itself. This outer product then produces a matrix. The matrix, the long name for it is a variance-covariance matrix. Sometimes we leave off the variance and just call it a covariance matrix. Since the diagonal elements of this matrix are equal to the variance of each individual random variable, and the off-diagonal elements are equal to the covariance. And it's symmetric because the lower and upper triangle of that matrix are equal, because the covariance of a random variable with another random variable is commutative. So the result of that is that we have a symmetric matrix that represents the variance-covariance matrix. Okay, now let's look at some specific and important distributions of random vectors. The first one is the multinomial. The multinomial is a straightforward generalization of the binomial. Recall in the binomial we had only two outcomes, 0 and 1. In the multinomial we can have a variety of different outcomes, and this allows us to represent a number of problems where we have more than two categories or two possible outcomes. So for example, a flip of a coin easily represented by a binomial, but the roll of a die is represented by a multinomial. And this can represent things like our example of admission to the University of Virginia. You can be admitted, waitlisted, or rejected. And so you have three possible outcomes, and that can be represented by the multinomial. So what the multinomial does is it looks at this random vector x, where each component of x represents the number of occurrences in that particular category. So again, if we think of our admissions, we could say X1 represents the number of people who were rejected, X2 represents the people on wait list, and X3 represents the number of people who were accepted. And there's a probability associated with each of those outcomes. So what the multinomial gives you is the number of occurrences in each one of those categories for n trials. And as you can see, the multinomial density function has each one of those probabilities taken to the power of the number of occurrences. So in other words, if we had the number of people who were waitlisted, that would be that x component, that x exponent, and the p would be 2 would be associated with the probability of being waitlisted. And what the factorial function in front of this density represents is the number of possible ways that we could observe those outcomes. Well, if the multinomial is a generalization of the binomial, the Dirichlet is a generalization of the beta distribution. And in this particular case, the Dirichlet distribution is over a random vector p, where each of these p's takes on values in the range from 0 to 1. And it's also the case that if we sum the p's, they're equal to 1. This means that, in fact, the Dirichlet, although it looks like it's in k dimensions, is actually in k minus 1 dimensions, because that summation requirement, that normalization requirement that it sums to 1, means that we actually have one less dimension that we're working with. And in fact, as we'll see, in 3 dimensions, if we had 3 outcomes, possible outcomes, then when we look at this, the space in which the Dirichlet exists in 3 dimensions, it really only exists in a 2-dimensional plane, and that 2-dimensional plane is called a simplex. It's a triangle of values, and we'll take a look at that in just a minute. Its parameters are alpha, this alpha vector, alpha 1 through alpha k. These alphas have to be strictly positive. And again, we have a normalizing function given by the gamma functions in front of the probability density for this random vector. And we have each one of the p components of that random vector taken to the value of their particular parameter, alpha 1, alpha 2, whatever. And that's the probability density function. When we look at the Dirichlet then in, as I said, in 3 space, and this happens to be the Dirichlet where alpha is equal to 1, alpha 1 is 1, alpha 2 is 1, alpha 3 is 1. We see the simplex, which is this triangle, this that exists within this space. And that's where all the points exist, is on this simplex. So in this case, it's very much like what we saw with the beta distribution. This is a flat or uniform distribution over the simplex. So any one of these points is equally likely to occur, is what it amounts to. And that means that over this surface, we get a representation that's fairly flat over that space. However, like the beta, we can get lots of different representations for a density function in that simplex. This one happens to be a unimodal one in which the alphas are equal to 10, and you can see that they're clustered toward the center of the simplex as opposed to the edges. But we can get something very much like that bathtub distribution that we saw with the beta. In this case, we can use values for alpha of 0.1, and we see we're at the edges of the simplex with very little likelihood of being toward the center. And we can even cluster towards one of the edges. We can get a variety of different shapes, just like we did with the beta distribution. Okay, the multivariate Gaussian is an extension of the Gaussian, the univariate Gaussian. Now we have a random vector, again, x, with 2 parameters, and the parameters in this case consist of a vector parameter mu, which is the location parameter for the multivariate Gaussian, and the covariance matrix, capital sigma. And with that, we get the density function that's shown with its classic quadratic form in the exponent. The shape of the multivariate Gaussian, again, looks like a little bell-shaped curve in multiple dimensions is what it amounts to. And as you slice through that, that plot, you can see that it's Gaussian in a univariate sense. So on the left, you have a contour plot showing the contours of a sampling of a multivariate Gaussian, and on the right, you have a surface plot. And in both cases, you get the impression of what's going on, that it's these bell-shaped curves, very much like the univariate Gaussian in one space. So slicing through that surface, you get that univariate Gaussian shape. And this is again a very useful distribution. It's used widely, as we will see, as a way to describe uncertainty in a number of problems. The t-distribution also has a multivariate extension, and it's very similar to the multivariate Gaussian. Again, we have a random vector x, in this case of k components. We have a location parameter. So just like we had three parameters for the t-distribution, the univariate t-distribution, now we have three parameters as well, but in this case, there are two of them. Well, one of them is a vector, one of them is a matrix, and one of them remains a scalar. So the vector is the location, which is given by mu. So it's a vector parameter. We also have a matrix parameter, which is called the shape or scale matrix. And then we have the scalar parameter, which is still the degrees of freedom. And the probability density function is as shown. When we look at the multivariate t, it has, again, much broader tails than what you get in the multivariate Gaussian. And you can see that when you look at how broad the range is. This is a multivariate t with 2 degrees of freedom. It's spiked a bit at right around 0, 0, 0 in this two-dimensional space that's shown. And this, again, is a contour plot. But you can see when you look at the range on those x and y axes how broad the tails go for this multivariate t distribution. You can see it more clearly possibly when we look at this multivariate t distribution with 10 degrees of freedom. At 10 degrees, it's approaching a shape that's looking a lot more like a Gaussian, but it's still much broader than you can see that by seeing how wide the distribution is compared to the Gaussian. So the t distribution on the left with 10 degrees of freedom and the Gaussian distribution on the right. Okay, the final distribution that we'll look at is the Wishart. And the Wishart is an important distribution for us because it is the only distribution that we will use that actually considers random matrices as opposed to random vectors. And if you look, these random matrices are composed of the outer product of a series of random vectors. So we form our random matrices through that outer product of random vectors. And then given that, we can find a distribution, a probability density function for these random matrices. This gives us a tremendous amount of flexibility to handle a variety of problems. For those of you that are interested in deep learning, this is the kind of thing that allows you to look at these matrix kinds of operations that occur within deep learning algorithms. But we'll find it very useful for us as well as we model a variety of problems in uncertainty. So this is, it looks like a complicated density function, but in fact we'll find it quite useful for us when we need to handle random matrices as opposed to random vectors.